Good morning, ladies. How are you? Okay, so today we will finalize this lesson. Still only the last part, which is a parabolic about parabolic mirrors and spherical aberration. Okay, already we're done with concave mirrors and convex mirrors. So this is the last part. At the beginning of the lesson, we talked about a phenomenon called spherical aberration. What is spherical aberration? We said spherical aberration, it happens with spherical mirrors like concave. So for sure, girls, concave and convex, both of them are called spherical mirrors. Concave, it's called concave spherical mirror. Convex, it's called convex spherical mirror. Okay, because they are section of a sphere. Okay, so here we have a concave spherical mirror. As you can see here, not all the rays they intersect after reflection at the focal point. Okay, so once we see the rays are coming parallel to each other, where is our object? It means our object is at infinity, our object is very far. When these rays hit the mirror, they converge. Okay, the rays that are close to the mirror, as you can see this one, it's close to the mirror, it hits the mirror and it reflects by passing through F. And this one also parallel, it hits close, it hits the mirror and it reflects by passing through F. But the rays that are far from the principal axis, which is in black here, they reflect by passing like through a point which is more near to the mirror than the focal point. Okay, so again, using a concave mirror, the rays that are far from the principal axis, they do not intersect exactly at the focal point, which causes what? A blurred image, not a focused or clear image. So to avoid this phenomenon, this spherical aberration, this problem, okay, in some important devices, for example like telescopes, what do we use? So we use something called parabolic mirror. So the parabolic mirror now, it from its name, it's a section of parabola, not like spherical mirror. So spherical mirror, it was section of sphere. Here it is section of parabola. So here, whatever the rays are like far or near to the principal axis, they all pass through F after reflection. So parabolic mirrors eliminate this problem and produce sharper image, clearer. Okay. So parabolic mirrors, rays that hit spherical mirrors far away from the principal axis, so PA, here I mean by it the principal axis, often reflect through different points, causing fuzzy image or blurred image. This is known as spherical aberration. Okay, but this happens with what? When using the spherical mirror. To eliminate or to avoid this spherical aberration, we said we will use parabolic mirrors. Okay, thus, a ray traveling parallel to the principal axis of a parabolic mirror is brought to a focus at the same point F, no matter how far the ray is from the axis. So here it doesn't matter if the ray is near or far from the axis, because we are using parabolic mirror. Okay, so since the path of a light ray is completely reversible, here pay attention here, it follows that a light source placed at the focus point F of a parabolic mirror, it gives you a perfectly parallel beam of light after the light has reflected off the surface of the mirror. Type. Let's understand this sentence. What is it? See here. They are saying that now if our object is not very far, if our object is placed here at the focal point, at the focus, so the rays will start from the object. They will hit the mirror and they will reflect how? Parallel, because light is reversible, is able to be reversed. So we have the opposite situation. Okay, we are saying, suppose now we have the object here at the focal point, not very far. So the object at the focal point, so incident rays are the rays coming from the object, hitting the mirror and reflecting. How do they reflect? They reflect parallel. So if you want to get a perfect parallel beam of light, it's useful to use an object, a lamp for example, and you place it at the focal point, okay, in front of a parabolic mirror. okay, instead of spherical. So this like what? This is like for example the headlight. So see, a car headlight consists of light bulbs. There is light bulb which is placed at the focus of parabolic reflector. In like you have a reflector like a mirror, and you place at its focal point the bulb, so the rays coming from the bulb will hit the mirror and reflect parallel. The use of a parabolic reflector enables the headlight to cast a very straight beam of light ahead of the car. Okay, another use. What do you expect? So already we talked about receiving dishes, satellite. We said that satellite, it has the shape of a concave mirror, but if we want to get now a better and better result in focusing all the radio waves, for example, we can use, instead of spherical receiving dish, we can use a parabolic. So see, the receiving dishes of radio telescopes are generally parabolic. They reflect the incoming radio waves. So radio waves are coming from very far distance. They are coming parallel because they are traveling very far distance. So when they hit the parabolic mirror, they reflect inward, they converge, and they intersect, all of them exactly at the focal point. And at this focal point, what do we place? We place the receiver. And like in this way, so like girls, we gather lots of radio waves in one point, in exactly one point. So this will give us for sure more focus and bring them to a focus at a single point where the detector or receiver is placed. Okay, so it is so parabolic mirror actually are more difficult, and therefore they are more expensive to make than spherical mirror, because they give us a sharper and a clearer image. Okay, so here again, so this is a spherical mirror and this is what a parabolic mirror. See how here the spherical mirror, the rays, they do not all, the rays that are far from the principal axis, they intersect here, okay, but the ray here, all the rays that are near and the rays that are far, they intersect all at focal point. So only parallel rays close to the principal axis of a spherical mirror will converge at the focal point. Only the rays that are close. Okay, rays farther away will converge at a point where, see, closer to the mirror. The image formed by a large spherical mirror will be then a disk, not one point, because I have here intersection of some rays and here intersection of some rays, so the image will not be very sharp, will not be a point, it will be like a disk or like a blurred image. So this is known as spherical aberration. Parabolic mirrors don't have spherical aberration. They are used to focus rays from stars in a telescope. They can also be used in flashlights and headlights, since light source, which is if we place it at the focal point, it will reflect light in parallel, exactly parallel beam. However, perfectly parabolic mirrors are hard to make, and slight errors could lead to spherical aberration because they are not that easy to make this shape of parabola in a mirror. Okay, so also again the difference between them, this is here what you expect. If you see only the picture, if you compare between the pictures, you can know that this is spherical and this is what parabolic, because here the image, it's not a point exactly, here the image, it's a point. Here they are using lenses, not mirror, but the concept, it is the same. Okay, parallel rays converge at the focal point of a spherical mirror only if they are close to the principal axis. The image formed, then it is, as we said, disk, not a point. In parabolic mirrors, they have no aberration, no spherical aberration. The mirror focuses all rays at the same point, at focal point. That's why they are used in telescopes and light beams like flashlights and headlights. So the last thing I will show you today, it's an application of parabolic mirror. About parabolic mirror, in a device called reflecting telescope. We have actually two types of telescopes. We have type called reflecting. This type, we'll talk about it in this lesson. We have another type called refracting telescope. We will see it in the next chapter. So reflecting telescope, it means it's based on mirrors, on reflection, okay? But the refracting telescope, you will see in the next chapter that it's based on lenses, therefore like refraction. Okay, so
a reflecting telescope works by gathering light using a concave mirror and then directing that light through the eyepiece. Parallel light rays pass down the barrel of the telescope and are reflected by the parabolic objective mirror at the telescope's base. These rays converge toward the objective mirror's focal point, F, where a real image would normally form. However, a small curved mirror that lies in the path of the light rays reflects the light back toward the center of the objective mirror. The light then passes through a very small hole in the center of the objective mirror and comes to a focus at point A. An eyepiece near point A magnifies the image. It is interesting to note that the small mirror and the hole in the parabolic objective mirror do not block out or mask any part of the image. However, they do reduce its brightness slightly.